So we are on the numerical techniques of unsteady problems. Okay, and yesterday we were at a point where we simply looked at forward difference in time and central difference in space. You remember that? What was the equation? We were talking about 1D unsteady heat transfer. I told you I would solve one problem, so let's solve it first, and then I would give you a little introduction about the 2D problems, the implicit techniques which you can use over there, and then I would just you can say show you few MATLAB codes. Okay, and I would discuss how you can apply those codes to look at the problems, different problems related to heat transfer. So anyways, this was partial T by partial T equals alpha partial square T by partial x square. Okay, so that was the equation, and we came up with something Tin plus 1 minus Tin over delta T, and then you have alpha, and then you have what? Ti plus 1 n minus 2 Tin plus Ti minus 1 n over del x square. Okay, so this is the unknown. This is the quantity which is to be found out, Tin plus 1. Now all other terms, they are from nth time level. Okay, so now by the way, how many boundary conditions do you require to solve this problem? 2 boundary conditions, because it is second order in time. And then how many initial conditions do you require? 1 initial condition, because it is first order in time. Okay, so then I would say that just keep that unknown term on the left hand side and all other terms on the right hand side. So that would come out just like this: alpha delta T by del x square, and all other terms they could be written over there, Ti plus 1 n minus 2 Ti n so that was Ti minus 1 n, right? So let's say we were let's take that example of a rod. Can you see that? Okay, that color can be seen. Oh, I'm sorry. So let's say this is a rod, and I'm just considering 1D heat transfer, and let's divide this rod into equally spaced nodes, right? And the number of nodes on this rod, they are 5. Okay, so this is a schematic for an example which represents a 1D unsteady heat transfer. Now for this problem, I say that this is node 1, this is 2, this is 3, 4 and 5. Let's say L is equal to 1 meter. The total length is 1 meter. Okay, and delta x is equal to, if we divide it by delta x, how much it would be? 0.25, 0.25, 0.25, 0.25, right? So this would be 0.25 meter delta x. And then let's say delta t can be taken as, for example, let's take it as 0.1 meter. Okay, sorry, 0.1 second, I'm sorry, 0.1 second. And then alpha can be taken as 1 unit, whatever the unit is. This is 1 unit, right? Now I assume that t at x is equal to 0 and all time that is equal to 25 degrees centigrade, for example 25 degrees centigrade. It means at all the times at this t where x is equal to 0, and as you move along it you come at x is equal to L at node 5, and at all the time you have 25 degrees centigrade. Okay, and then at t x is equal to L and all the time t, let's say your temperature was 5 degrees centigrade, for example. Okay, and let's change its unit. What would it be? 298 Kelvin, and this would be what, 278 Kelvin, right? So let's use the SI units. And then at all the x except those two nodes, the boundaries except those two nodes, so I should use this thing to be more appropriate, except x lesser than is greater than 0 and less than L, mathematically I can write it, and at time equals 0. Let's say the initial conditions are 0 degrees centigrade and I just put it like 273 Kelvin. Okay, and my point is you have to find out temperature at all the nodes. By the way, can you see it at the back? Yes. Okay, so find out temperature at all the nodes. All the nodes means there are 3 unknown nodes, because those two boundary nodes, they would have the same temperature all the time. At all the nodes as you progress in time. I am not specifying any time because it is just a general question, so as you progress in time. But in your assignment you might have seen that I have asked you to provide the temperature details at a certain time. It means you have to go through a certain number of time levels and then you would come up with the solution. Anyways, so what can I say? It means at n is equal to 1, n is equal to 1 represents the initial time. Generally it is taken as n is equal to 0, but you can take it as n is equal to 1, no problem at all. Time equals 0, initial time, right? So T10 was what? Just look at that. T10 was what? 298 Kelvin, right? And then what is T20? It is 0, so it is 273 Kelvin. What is T30? Sorry, I am taking it as 1, so let me take it as 1. By the way, this is representing an initial condition. So this is again 273 Kelvin, and then you have T41. This is again 273 Kelvin, and then what about that T51? It should be 278, isn't it? Why? Because this node number 5 is the last node, which is the boundary node. So this is 278 Kelvin. You understand that? What should be 0? You are talking about this index? Oh, this index is something else. This is just number of time step. This is first number of time step, first time step, right? I am taking the first time step at time equals 0. Physical time is something else. Let's say if I ask you what would be the time at n is equal to 2, what would be time? Just look at this slide and tell me. What would be the physical time at n is equal to 2? It should be 0.1 second. Why? Because you are moving forward with a time difference of 0.1. It means you see a picture at 0 second and then you see the next picture at 0.1 second. You see the next picture at 0.2 second. Okay, so that's how you go. We are using indices. Now, by the way, why we are using indices? Because you have to write all the codes on the computer, right? You don't have any functional dependence of temperature on time and x. So you have to play with I and j. You remember those for loops and all those other loops where you represent, okay, this is the first point, this is the second point, this is the third point, right? So you use those indices. This is number 1, this is number 2. So you basically, these are the addresses of all the points. Anyways, let's move forward. So I say that let's find out all the temperatures at n is equal to 2. And what would be time, physical time at n is equal to 2? It should be 0.1 second. Why? Because I am considering the first time instant at time is equal to 0. Right? So it is just a matter of notation. If you put it 0, no problem at all. Right? But just to give you an idea about the indices, I am using it like this. So time is equal to 0.1 second. So tell me, for example, if I ask you what is T2, T2, it means I am talking about the temperature of this node at time level 2. Just look at this finite difference equation. This says T2 at second time level would be equal to T2 at first time level plus this term multiply by T3 at first time level plus minus 2Ti. So it means 2 at the previous time level, which is time level 1, and then this plus Ti minus 1n, it means T1 at the previous time level. Okay, so let me write it down over there. This T2 T2 in the subspace at the second time level would be T2 at first time level. Remember this is not par, this is a superscript. Okay, and then plus and then you have alpha. I took it as 1, and what was delta T? It was 0.1, and what was delta X? It was 0.25 square, right? And then you have Ti plus 1n. What was Ti plus 1? Because I is at 2, so I plus 1 would be at 3, so this is 1. And then you have minus 2T, what? 2T1 plus T1, 1. So please plug in the values and tell me what would be T2 at time level 2. Please plug in the values and tell me. Okay, so this comes out to be 313 Kelvin. Fine. So let's now, because this is explicit scheme, you see the advantage that in just one equation we have come up with the answer for a certain node at a certain time level. So this is what is the advantage of the explicit scheme. But there is a disadvantage, and what is that disadvantage? Stability. You have to keep your delta T and delta X within a certain stability bound. Okay, and I have already told you what do you mean by that stability bound. So this is T3, 2. So this should be T3, 1 plus 0.1 over 0.25 square. This should be T what? 4, 1 minus 2T3, 1 minus T2, 1. Oh, sorry. Yes, this is plus. So can you please give me the number? So this comes out to be still it is 273 Kelvin. Okay, and then let's say, because I just want to solve the whole problem for at least 1 to 2 iterations, so that's why I'm taking time for this, so that you can understand. And then I would plot few plots as well. I would show you few graphs, and then let's say this is T4, 1 plus 0.1 over 0.25 square, and this would be T5 1 minus 2T4 1 plus T3 1. sorry, just I don't have a calculator, so that's why number crunching is with you guys. This your responsibility is to give me the correct answer. What is the value?
281.
This is 281 Kelvin. So are you sure about this number? Come on, don't tell me. Just like
281.
no, the answer for T42 is 281. And what about T32? Okay, this whole temperature becomes 0. Okay, so right, I understand that. So anyways, this is 281. But the point is, have you put this value at 278 degrees centigrade? This value at 278. Did you use that value? Okay, just look at it very carefully. Now, why I'm putting some doubts on your calculation. Just see. For example, I plot temperature with respect to time. Not with respect to time. Let's say this is x. Okay, and this is x equals 0. This is node 2, 3, 4, and 5. Now, what is the initial condition at node equals 1? Sorry? That was 298. Okay. This is 298. Let's say this is 298. Okay. And then what is this value? No, I'm talking about n is equal to 2. Sorry? 313. So this is 313. And then what is this value? Again, this is somewhere here. This is 298, so this may be 273. And then this value? So it may be somewhere here. And then this is? Do you think it goes like this? Like, for example, one temperature node is, like, just see and try to find out the error where we are doing something wrong. Okay, just let me give you the whole values. At n is equal to 1, just a minute. N is equal to 1. This value is what? This value is 273. This is 273. This is also 273, and this is okay. And at the very next time level, at n is equal to 2, this is what? Okay, this is 278. You say that it is what? This is, and this is. Does it look physically correct? So this value, I am just talking about the validity of your value. Just check the number. Is it physically correct? Can you understand my point? Why I am putting some doubts on your calculation? Like, can this temperature be going from 273 to 281 when the surrounding temperature is 278 and 273? Heat should flow from this side to this side. That's what you can understand. Okay, so that's how you analyze your numbers. Why I'm sorry? Sorry? Yeah, exactly. So because temperature, heat is going from this side to this side, so it should gradually evolve, isn't it? It should gradually evolve because this is time. We are basically making no mistake in the physical modeling of the system, but there is some problem with this number. Yeah, exactly. It should not be going like this. So my point is, where is the error? Can you please check your calculations once again? And let's check this stability criteria. partial delta T by del x square. What was the value? This was 1. This was what? So that number comes out to be, sorry, no, that number, okay, this number comes out to be 1.6. Now this is the error. You understand that? So your alpha delta T by del x square is not in the stability bound. So it means you created a disturbance. Now look at this very carefully. I try to give you the physical significance of this point. Just see, when the temperatures are changed over there, so what you are trying to do? You are trying to perturb the system. You are trying to disturb the system. Okay? And it has to be within a certain stability bound. Now what is going on? Physically, did the system look stable? I mean, it is giving you physically incorrect value, right? So it means the error, a small error or a small disturbance is growing. It is not suppressed by the system, right? If that error is growing, now just go to the next level. Okay, let's do the second time step, third time step. At n is equal to 3, let's do it this way. What should be the value at t2 comma 3? It should be like t2 comma 2 plus alpha delta t by del x square. You already have said that this is 1.6, and then this is t3 comma 2 minus 2t2 comma 2 plus t1 comma 2. Can you give me this value? It is what? 225 Kelvin. Now you see it has come down from a 3132. Now you see, is there anything like 225 at the boundaries? I mean, if you look at the problem physically, those boundaries having 298 and 273, and all the interior nodes should have temperature between 298 and 273, isn't it? The point closer to 298, it may have a temperature of, let's say, 290. The point closer to the second end at 273 degrees centigrade, that point number 4, that may have a temperature of, let's say, 275 or 278 degrees centigrade. You understand that? So there is, you see, there is a fluctuation, large fluctuation. Temperature has gone down. So you remember that plot which I showed you in the stability discussion, that it was at 273, then it was at 298, then it comes down to 225. Is it possible to have that? So it is a non-physical solution. You see, that's how stability conditions, they just give you wrong results. Have I clarified my point? Yes, so you see, and it would keep fluctuating like this. It would keep fluctuating like this, and suddenly it would grow. At, let's say, at T2 temperature with respect to time. Now, do you understand the physical and the computational meaning of stability? Right? Now, let's say, let's change the values, and my point is, let's take that alpha delta T by del x square, just irrespective of delta T and del x square. I am just giving you a value of, let's say, 0.1. Just take this value at 0.1 and find out all the unknown nodes at t equals 2. So this should come out to be 0.1. Let's say the whole value is 0.1. This may be t3 comma 1 minus 2t comma 1 plus t1 comma 1. Okay. Now we are basically keeping all the parameters in the stability, within the stability bounds. Okay. And then we repeat the calculation. See what is the value. What is the value for T2 comma 2? 275 point. Okay, this is 275.5 Kelvin. What is T3 comma 2? This is 273. Okay, and what about t4 comma 2? It is 273. So now it looks what? Physically correct. You understand that? Okay, for clarity, let's find out the temperature at n equals 3. Just find out temperature at T2 comma 3. So this should be T2 comma 2 plus 0.1, and then you have T3 comma 2 minus 2T comma 2 plus T1 comma 2. What is the value? Come on. What is T2 at third time level? Keep all the values from the second time level on the right hand side. Sorry? Okay, what about T3 comma 2? Oh, sorry, this is 3 comma 3. Sorry? This what? You are talking about T2 or T3? T2, 3. Yes, it should be lesser. Why? Because heat is flowing to that point. Heat is still flowing to that point. Okay. So just give me the value. What is the value over there? .273 point. Now you see that it is evolving with respect to time. Initially it was 273. At the first time level there was no change in the temperature. Why? Because the heat which has starting flowing from this point, from the right end to the left end, it has not reached to that point. It has not reached to that point. You understand that, right? And this point, which is adjacent to node number 5, like the node number 4, it is also adjusting its point. Initially, just look at that. What was its temperature initially? 278, and this was 273. So obviously heat would also start flowing from this point to this point, isn't it? Heat would start flowing from this point to this point. That is why it is increasing with time, 273. But there would be a time when this temperature would increase from this one and heat would have only one direction. You understand that? So that's how you should analyze your numbers. So using ANSYS or Fluent does not mean that you just create a random mesh, give some random value. So those softwares are just like garbage in, garbage out. If you plug in the garbage, it would give you the garbage, and you would be scratching your head in defining the physical meaning of that result. Okay, so I hope you understand what do you mean by stability. So you are quite clear about the stability, and I have also solved one example. And by the way, if you want to look at the physical interpretation, or we always tend to use, as engineers, we always tend to use this plot. Let's say on this side we have, so this is node 0, sorry, this is node 1, this is node 2, 3, 4 and 5. Let's say initially this temperature was 298 and this temperature was what, 278, and all the other temperatures are 273, for example. So this is the curve for time equals 0 second. So in time you would see that it would evolve. It would go like this. Although endpoints would remain the same. Why? Because these are the boundary conditions. So this curve, the second curve would be for t equals 0.1 second. You go for the other curve and it would basically, let's say you may have another curve just very close to this one. I'm sorry for that. It may go like this at t equals, let's say, 0.2 second. And there would be a point when you change the time level but the temperature values would remain the same. So that is the point which is known as steady state. You understand that? Is there any question from your side regarding this stability and this scheme? No, diffusion number is something which is the material constant, alpha. But alpha delta T by del x square as a whole, this term should be less than the stability bound. I think this is 1/2 or 1/4 in this case. 1/2. Okay, so as a whole. So for example, if your alpha is much larger, you need to keep your delta x larger as well. Larger, right? And you need to keep your delta t very small. You understand that? Right? So you need to look at the whole parameter, alpha delta t by del x square. If exactly, it would evolve as a physically correct system, physically correct problem, you can say. It would evolve as just like this. And I hope you understand what do you mean by stability. If the system is not stable, it would keep fluctuating. You see that the temperature has gone from 273 to 313 and then it has come down to 225. So it is fluctuating. And suddenly you would see that the temperature would come out as if like 10 raised to power 19 or 10 raised to power 20. Okay, so this is problematic. So 1D problems, we are done with it. Let me just write down this unsteady (2D) heat transfer. Okay, is there any question?
So how to identify a stable system? You just saw the values and said it was unstable. Is there some other way?
Yeah, because I can just see the fluctuation. I can just see the fluctuation, and I know from the stability bound that it would be that error would be growing. The system would become unstable. Let's say you would be getting those infinite values, larger values, 10 raised to power 7, 10 raised to power 8, after certain, let's say 2-3 time steps. That would happen all the time. But if you look at the physically stable system, I repeat my discussion just to answer your question. What do you mean physically? For example, there is a bus. Let's say you are riding a vehicle and it has gone through a jump. This speed breaker kind of thing. You are coming from this side and this is a speed breaker. Okay, and I just try to plot your y displacement. You see, due to the damping and the suspension, it goes like this. But if you are on a Sohrab bicycle, what would happen? Thuk, right? So it means that is not providing you any kind of damping. Okay, but if you are basically in riding a good vehicle, let's say Honda Civic or let's say Mercedes or whatever, so what you would be getting? You would be getting small oscillation and then it would come to rest. It would come to rest, isn't it? So this is what is stability. And passing the vehicle on this speed breaker, I would say this is disturbance. Or this is, let's say, perturbation. Okay, so this is disturbance or perturbation. Why? Because vehicle has been disturbed from its initial state. Now the problem is, before coming on to this speed breaker, vehicle was initially at y equals 0, for example. Obviously it is moving in x, but y was 0. And after going through that perturbation, would you able to achieve y equals 0 once again or not? If you are able to achieve that, it means your system is stable. If you are not able to achieve your initial state after going through that disturbance, it means your system is unstable.
Even on swap bicycle, you would achieve y equals to 0.
Sorry? Oh, I just gave that example for damping. I mean, there would be no damping at all. You would straight away come to 0. So would you like to be at y equals 0, let's say at the very next time level? Not at all. If there is some disturbance, there should be a damping. Now you see, this is something which is damping. This oscillation kind of thing that is being provided, because this provides you comfort. So in your vibration or control systems course, you would see a lot of those discussions. Sorry? Sorry, alpha delta t by del x square, what should it be? And this is for what scheme? Once you take forward difference in time and central difference in space, and that is why this scheme is also known as FTCS, forward difference in time, central difference in space. Okay, now only at what? Not the diffusion number. Yes, alpha delta t by delta t. Yes, you can say that. If it is going beyond 1 by 2, you would say the system is going to be unstable. Why? Because with every numerical technique, whenever someone proposes some numerical technique, he would always suggest what would be the stability bound. And by the way, this is an important topic in the numerical analysis course, or let's say CFD course. How to find out stability bounds for a certain numerical scheme. And if you have some explicit scheme, you would say that obviously there would be a number for explicit scheme. And if you perform the same stability analysis for implicit schemes, that means the iterative schemes, you would come up with that number just greater than 0. Like that alpha delta t by del x square or alpha delta t by del y square, that number comes out to be greater than 0. So it means greater than 0. And I told you, accuracy is something else. More and more accuracy would be there if you keep your delta t and delta x very small. Now both of schemes, they have their own advantages. Both of those schemes, they have their own advantages. Like for example, those iterative schemes, they won't provide you any stability limit, so you can keep anything like delta t, delta x. You just need to have rough values, guessed values, not the guessed values, crude values. You don't need to be very accurate, but you just need what would happen. You just need to have an idea. Okay, go for that iterative technique, right? But if you want to be more accurate, let's say this is my question. This is my perspective. If you want to be more accurate, and you know that to be more accurate, you have to keep your delta t and delta x very small. So you should go for explicit schemes, isn't it? Why? Because if you go for the implicit scheme, I would show you how you can implement that implicit scheme in time domain in unsteady problems. So. No. That stability is something else. Accuracy is something else. Now, what do you mean by accuracy? For example, if I ask you, okay, I would just, I would not solve this system, but I would just give you a hint because I need to complete the lecture. Okay, so just look at that. If I say this was 0.1, just find out temperature values at t equals 1 second. I am giving you a physical time. Right? Just make this parameter equals 0.1, select any delta t and perform your calculations till you reach t equals 1 second. And see the value of any node, see the value of the temperature at any node. Okay. Now, just change this value to 0.01 second. Your delta t would be even smaller. 10 times smaller, let's say I keep delta x and delta alpha, let's say that is the same. Just you have to perform, let's say 10 times more iterations or 100 times more iteration to reach that 1 second. Now just see what would be more accurate, what would be closer to the analytical solution. This value would take you to closer to the analytical solution, right? Just go there, just go back and check on the Google what is the analytical solution for 1D heat transfer. If you find any, just compare your numerical solutions with the analytical solution. You would see if you keep your delta T smaller, although it is stable, it is not fluctuating like this. But what do you mean by accuracy? For example, analytical solution needs to be here. Let's say analytical solution says that time is equal to 1 second, it should be here. And if you keep delta T very small, delta X very small, you would be somewhere here. So you can say your error 1 would be very small, right? But if you take alpha delta T by delta X square equals 0.1, for example, you may be here. Still it is stable, but this error has, now this is accuracy, this is not stability. You understand that? Now there are few other terms as well. I would not introduce you with those terms. If you get a chance to study CFD or numerical analysis, you would see those things. Okay, but these are just few terminologies. So your question. Half and 1. I'm sorry, I could not understand your question. This is alpha delta T by del X square. Okay, 0.5 and 1. Still it would be unstable. Right? Why? Because even if you go like this is what? This is 0.5. Even if you go to 0.51, you would see there would be instability. You would see that. Okay? So I hope I've made all the points clear. Now let's move on to the next part, which is 2D unsteady. Heat transfer. What is the governing equation? That governing equation is partial T by partial, this. So this would be alpha, and it should be partial square T by partial X square plus partial square T by partial Y square. You understand that? Now I hope, I think we would not have time for MATLAB in today's lecture, but we can cover it, no problem at all. We can cover it. And in the next class, I would try to at least show you few codes, just very quickly, okay, at the end of this class. So let me complete this first. This is alpha delta square T, partial square T by partial X square plus partial square T by partial Y square. So let's write down FTCS scheme for this problem. So this is forward in time. Now remember, how many dimensions are there? How many independent dimensions? X, Y and time. So how many indices should be there? 3. Okay, so let's say this is Tij n plus 1 minus Tij n over delta T should be equal to alpha Ti plus 1 j n minus 2 Tij n. I am using the same approach. There is just an introduction of one more index, plus Ti minus 1 j n over delta X square, and then the next term would be, now because we are taking time derivative with respect to Y, so this is Tij plus 1, Y index would be changing, minus 2 Tij n plus Tij minus 1 n over del Y square. Right? So you can keep this term on this side and you can have this Tij n plus 1. Now you see that instead of a one-dimensional rod, now you have a two-dimensional plate. So this may be the picture at time equals 0, and this may be the picture at time equals n delta t. Now you see, if n is equal to 1, let's say this is n equals 0 and this is n is equal to 1. So what would be time? If delta t is 0.1, your time would be 0.1 second. Okay, so you can describe your physical time just like this: the number of time step multiply by delta t, if you keep n equals 0 at the initial time, right? So that's how you can calculate the physical time. Okay, so this may be the second picture, and please try to develop a habit to analyze those numbers. This is very important. Okay, so similarly at the third time level you would be having another picture. And how many boundary conditions are required for this system? 4 boundary conditions: 1, 2, 3 and 4. And obviously you have to find out, let's say, those initial conditions for the unknown nodes. Understood? And you can apply the energy balance approach as well. How you can apply that energy balance approach? I have chosen one route, which was finite difference method, but let's apply that energy balance approach which we have been using previously. Let's say this is the cell. So we were talking about this physical time, and similarly if you talk about this thing, t equals 2 delta t. Now you see, physically you come up at t equals 0.2 second. So you have to look at, as far as that assignment is concerned, why I am discussing this thing, because I have given you an assignment. You have to look at temperatures at certain physical times. If you see that, I ask you to find out temperature at certain nodes at certain physical time. So how you can determine how many time steps you need to perform? Using this relation. You understand that? Okay. So this is about that explicit scheme. Again, let's talk about the implicit scheme. Let's do it this way. Let's start this implicit scheme from again 1D, a simple system. So this is node 1, 2, 3, 4 and 5. Okay, and this is delta x. Now what was the numerical technique? This was partial t by partial t equals what? Alpha partial square t by partial x square. Okay, now what would implicit scheme look like? This is tin plus 1 minus tin over delta t, and then on the right hand side, previously I took all the values at nth time level, the previous one. Now I am taking all the values at n plus 1 time level, the same time level. The same time level. Okay, so this is, let's say, ti plus 1 n plus 1 minus 2 n plus 1 plus ti minus 1 n plus 1 over delta x square. Now just look at that. You know the initial condition, you know the boundary condition, and all the values except this one are unknown. Now what you need to do? If there is more than one unknown in one equation, it means you have to use implicit scheme. You have to use what? Implicit scheme. Okay, and implicit schemes requires that you have to perform those certain number of iterations. Again the Jacobi method, again the Gauss-Seidel method. Okay, so let me use this value. Again, I am using the same initial condition, same boundary conditions. Okay, nothing different. So let's so I say that at time equals 0, for your understanding, now I change my stance that time equals 0, I have time n is equal to 0. So at n is equal to 1. Now, as far as this is the implicit scheme, you can take alpha delta t by del x square, any value of that parameter, and that value of parameter would not disturb the stability, it would disturb accuracy. You understand that? It would disturb accuracy. So n equals 1. Now, for example, just write down the equation for t2 equals 1. What would it would be? T2 equals t2 comma 0 plus alpha delta t by del x square, t3 comma 1 minus 2t comma 1 plus t1 comma 1. Was that the equation? Right? Similarly, just write down the equation for 3 comma 1. 3 comma 0 plus alpha delta t by del x square, 4 1 minus 2t 3 1 plus t2 1. Similarly, t4 1 equals t4 comma 0 alpha delta t by del x square, t5 comma 1 minus 2t4 1 plus t3 1. Now you see, all the unknowns are at time level 1, and each equation has more than one unknown. Now just tell me, how many unknowns are there? Just 1, 2, and this is the same unknown. So 2 unknowns are there. 1, 2 and the same unknown. So each equation carries more than one unknown. You only know the initial condition and the boundary condition. 2 boundary conditions, 1 initial condition. Because it is 1D unsteady problem. Okay. Now you see how you can find out all these values. Come on. So at each time level you have to go through few number of iterations. Now you see, in the explicit scheme, what did you do? You came up with the answer in one step. But in implicit scheme, you have to perform number of iterations. Now you see, at each time level, you have to go through that Jacobi method or Gauss-Seidel method again and again at each time level. And similarly, let's say you perform 100 iterations to reach your convergence criteria at n is equal to 1, and that n is equal to 2, you again do the same kind of thing. At n equals t, you again do the same kind of thing. Okay, so at every time level, you don't simply solve everything in one step. You have to go through few number of iterations all the time. At every time level. Now, I hope you understand that. You already know what is Jacobi method, what is Gauss-Seidel method. So you can employ those techniques at every time level. Similarly, this problem may become very cumbersome if you go for implicit scheme for 2D problems. What is the scheme? This is 1 over alpha partial t by partial t equals partial square t by partial x square plus partial square t by partial y square. Okay. Now 1 over alpha, I would use the same thing, and let me write down this equation: tij at n plus 1 minus tij at n over delta t equals, this term would become ti plus 1j at which time level? I am talking about the implicit scheme. It should be n plus 1. Okay, and then you have 2tij n plus 1 and then plus ti minus 1j at n plus 1 over del x square, and then you have plus on the same side, and this would be ti j plus 1 n plus 1 minus 2 tij n plus 1 plus Tij minus 1 n plus 1 over del y square, and this would be for a plate, and for any two-dimensional geometry. These four are the boundary conditions. You may have initial condition for all the unknown nodes inside the domain. Go through each few number of iterations all the time, and those iterations can be performed by, let's say, Jacobi method or the Gauss-Seidel method. Okay. So I told you just one method as far as those solution through Jacobi and Gauss-Seidel methods are concerned. You have to solve the equation every time, but you can construct a matrix as well for those equations. Okay. How I would not tell you because it may be slightly advanced, but I just want you to learn how to solve those equations. That's it. Okay. Any problem about this implicit scheme? Now you see, for example, did any one of you experience any kind of Fluent or let's say ANSYS or any other software? You have used that? Okay, you might be selecting those numerical techniques. This is first order, this is second order. If you go for few terms, let's say unsteady term and the momentum term, diffusive term, right? So once you select those terms, you have to be very careful about the stability technique. Okay, you guys would be doing that CAE course as well. Okay, in that course, remember this thing, that don't just select all the values of delta x and delta y randomly. If you are interested in choosing any specific scheme and that is explicit, make sure that you know what is the stability. And that's how you can only look at those physically correct analytical description. There is a meaning with every number. To come up with a number, it's not a big deal. But to come up a physically correct number, that's the sole objective.
So accuracy is second priority.
No, accuracy is the first priority. Why? Because if you basically keep everything in stability bounds, you would see that your accuracy you have to be within the stability bounds. Like for example, so any other question? No? So this numerical technique is completed from my side. Done. Now we can move on to MATLAB. Okay. Okay, so because there is a question about the energy balance method, application of the energy balance method as far as those problems are concerned. So let me answer that. This is the plate, and for example, let's say I consider this to be the cell. There is another point, then there is another point, then there is another point, and then there is another point. For energy balance, what you do, you can assume that all the energies are going in. I assume there is no heat generation within that cell. I can take that Q dot G term is equal to 0. And then what is on the right hand side? Energy storage term, isn't it? How you can write this energy in term? This should be Q1 dot plus Q2 dot plus Q3 dot. You can write it plus Q4 dot. You can write it. The only thing which is coming in is this term. What is that? 1 over alpha? Is that 1 over alpha? Okay. And then this is partial T by partial, right? And similarly, because this is partial T by partial T, for example, this is at nth time level 0, and you want to find out your value at nth time level equals 1, for example. So you would take a difference of this value and this value. 1 over alpha Tij, let's say n plus 1 minus Tij n over delta T. And these terms you can already know. Similarly, for example, if I say that this is something where I want to find out the temperature and there is convection over there, let's say. So from one side there is a convection. You understand that, right? And you can write, let's say this Q2 would be of the convection part. If that is adiabatic, so still you can say, okay, this is Q2 is equal to 0. So that's how you can apply that energy balance approach. Okay, so it's your choice. I have given you both of those, finite difference and energy balance, till the time I specify it that use this scheme. Just like in the previous quiz, I asked you to go for the energy balance approach, right? Otherwise, it is a kind of finite difference approach. Once you talk in terms of Ti plus 1 minus Ti, it is a finite difference, but it is just, you can say, because we are applying the principle of conservation of energy, so we say that it is an energy balance approach. Otherwise, it's one form of finite difference, no problem at all. Yeah. Finite difference is based upon what? Yes, but finite difference is something which is a numerical term. You can use the same finite difference approaches for, let's say, any equation. For example, if I ask you that partial u by partial t equals 1 by something, some parameter, partial square u by partial x square, and I say this is one equation, can you apply FTCS scheme over there? You can apply that, but would it be like energy balance? Not at all. Okay, this is some other equation. This is physical description of this equation is something else. Okay, any other question? So let's talk about this MATLAB thing. If you look at MATLAB, structure of MATLAB, to be very specific, MATLAB is for matrix laboratory. You do anything in MATLAB, anything, may it be related to control, optimization, heat transfer, whatever. It would give you no error. I'm not talking about the physics, I'm just talking about the mathematics and the relevant coding problems. It would not give you any error as far as you are following the rules of linear algebra, matrix algebra. Like for example, if there is a certain rule regarding multiplication of matrices, right? So if you are not violating that principle for the matrix algebra, where you have to keep a certain number of rows and certain number of columns in each of those matrices, right? So that MATLAB would perform that step for you, no problem at all. So if you see that, I say A equals 1 and A is equal to 1, for you it is a scalar, but for MATLAB it is what? It's a matrix. It's a matrix of size 1 by 1. Okay, for example, if I say that, okay, size equals A. Oh. Okay, just see that. Once I'm not going to give you the details of those commands. They are available in any book. You can go to the library and see there are a number of books regarding MATLAB introduction. You can have any book. But my point is how you can use this MATLAB as far as though that heat transfer problem is concerned. Okay, heat transfer problem. So if you look at size of A, size of a matrix, its size of the matrix is 1, 1. And for example, I just describe another matrix 1, 2, 3, 4. Just see how does it look like. 1, 2, and if I want to switch to the next row, I would give what is that? Is it a semicolon or colon? It's a semicolon. Okay, so you give a semicolon and you switch to the next row. You understand that? Okay, let me take another matrix. I say that this is 3, 4, 5 and 6, 7, 8. Fine. And I say that, okay, perform an iteration for C equals A multiplied by B. I come up with some number. right? And for example, if you say you see, you would have that error. Why? Because you are violating a rule in matrix algebra. You understand that? So you can see, as far as that introduction is concerned, introduction related to different commands, size of A, length of A. If you want to go for it, fine. You can have that introductory MATLAB book over there, or you can find few lectures on MATLAB on YouTube as well. Okay, so you can see those lectures. But if you have any question, you can always come to my office, no problem at all, right? But my point is to implement one scheme, one numerical scheme for heat transfer problem. Now there are few things regarding coding. You have already done that in your